There is a planet hiding in plain sight, orbiting one of the most famous young stars in the sky. For more than a decade, astronomers had looked at the Beta Pictoris system and seen a bright disk of dust, two known worlds, and the restless architecture of a planetary system still under construction. But buried inside old observations was a third planet, faint, close to its star, and almost impossible to separate from the glare. The discovery is a reminder that astronomy is not always about looking farther. Sometimes, the universe has already left the evidence in our archives. We simply need better questions, better instruments, and the patience to look again. Beta Pictoris is about 63 light-years from Earth, in the southern constellation Pictor. That may sound distant, but on a galactic scale it is practically next door. The star itself is young, only around 20 million years old, and it is more massive and hotter than our Sun. What makes Beta Pictoris special is not just the star. Surrounding it is a broad, tilted disk of gas, dust, ice, and rocky debris. This is the raw material from which planets form. In our own solar system, the planets emerged from a disk like this more than 4 billion years ago. Around Beta Pictoris, we are watching a similar process while it is still young, violent, and unfinished. The disk is not smooth. It contains warps, clumps, evaporating comets, and signs that gravity is rearranging the debris. Those disturbances are clues. A planet may be invisible, yet its pull can sculpt the material around it, leaving a gravitational fingerprint in dust and ice. Astronomers already knew that Beta Pictoris hosts a giant planet called Beta Pictoris b. It is several times more massive than Jupiter and travels on a wide orbit, far enough from its star that powerful telescopes can sometimes image it directly. A second planet, Beta Pictoris c, was detected through the star's subtle motion, the tiny wobble caused by an orbiting companion. The newly revealed world is different. It is much fainter and much closer to Beta Pictoris. From Earth, the star overwhelms the planet by an enormous factor. Trying to see the planet is like trying to spot a candle flame beside a stadium floodlight, from dozens of light-years away. This is where the James Webb Space Telescope changes the story. Webb observes infrared light, wavelengths that can reveal the heat of young planets. It also carries instruments capable of separating a planet's spectrum from the bright, structured glare of its host star. In this case, the key was not a simple snapshot. The planet had been hiding in data collected years earlier. Researchers developed new ways to model the light from the star and the surrounding disk, then searched for a source that moved exactly as a planet should move along its orbit. The signal was delicate. A false feature can appear when starlight scatters inside a telescope, when the disk has an unexpected shape, or when data from different observing modes are combined. A real planet must survive every test, its position must be consistent, its motion must make sense, and its light must have the physical signature expected from a young world. The result points to a third planet in the Beta Pictoris system, one that had escaped detection for roughly 11 years. Its faintness is not evidence that the planet is unimportant. In fact, its difficult location makes it especially valuable. It occupies the region where the architecture of the system becomes complicated, where planets, dust, and migrating debris all compete to shape one another. Think of the system as a cosmic construction site. The outer giant planet acts like a massive bulldozer, clearing and disturbing material along its orbit. The inner planets move through a denser environment, surrounded by the leftovers of formation, collisions, fragments, and icy bodies. Every orbit changes the distribution of debris, and every cloud of debris records the history of those gravitational interactions. A hidden planet can help explain why the disk looks warped or why certain dust features appear in particular locations. It can also tell astronomers how quickly young planetary systems settle into the ordered patterns we see around older stars. The timing matters. At only about 20 million years old, Beta Pictoris is young enough to preserve the memory of planet formation, but old enough for recognizable planets to have assembled. It is a transition zone between a chaotic disk of material and a mature planetary system. Our own solar system probably passed through a similar phase. Early Jupiter and Saturn may have shifted their positions. Uranus and Neptune may have migrated outward. Comets were scattered, planetary embryos collided, and debris was gradually swept into belts or thrown into interstellar space. We cannot travel back 4 billion years to watch that happen here. But Beta Pictoris offers a living comparison. Its planets are not replicas of ours, and its star is different from the Sun, yet the same laws of gravity, radiation, and orbital motion operate there. The discovery also illustrates why direct imaging is so difficult. Most exoplanets are found indirectly. Astronomers watch for a periodic dip in starlight when a planet crosses the face of its star, or they measure the star's reflex motion as the planet pulls on it. These techniques are extraordinarily productive, but they tell us about a planet through its effect on the star. Direct imaging is more like taking a portrait. The reward is a planet's own light. For young giant worlds, that light can reveal temperature, clouds, chemistry, and the history of how the planet formed. But the planet must be far enough from its star to be separated, bright enough to detect, and observed with instruments precise enough to suppress the star's glare. Beta Pictoris sits near the limit of those conditions. Its dusty disk is both a challenge and an advantage. The disk adds confusion, but it also provides context. A planet is not just a point of light, it is one piece of a much larger system. The new observations show how modern astronomy increasingly depends on archives. Telescopes collect more data than any individual team can fully analyze at the moment of observation. Years later, improved algorithms and a new scientific hypothesis can turn a buried pattern into a discovery. This is happening across astronomy. Old images are reprocessed with sharper calibration. Machine learning systems search for faint companions. Spectra are compared across epochs to identify motion. A dataset can become more scientifically powerful without changing a single photon, because our ability to interpret it has changed. But algorithms do not replace judgment. They generate candidates, not certainty. Astronomers must understand the instrument, the star, the disk, and the possible ways noise can imitate a planet. Confirmation comes from agreement between independent observations and from a physical explanation that fits all the evidence. That standard is important because the universe is full of optical illusions. A dust knot can look like a planet. A background star can appear close to the target. A processing artifact can vanish when the data are reduced in a different way. A convincing discovery is one that becomes stronger when the analysis is challenged. The hidden world around Beta Pictoris is exciting for another reason: it expands the known planetary inventory of a system that has already become a laboratory. With 3 planets and an enormous debris disk, Beta Pictoris lets scientists compare planetary mass, orbital distance, brightness, and gravitational influence within the same young environment. That comparison may reveal whether the planets formed where we see them or moved there later. It may show how giant planets interact with smaller worlds. It may explain why some young systems retain thick disks while others clear their material quickly. The faint planet could also become a target for future observations. As Webb and other observatories return to the system, astronomers can measure its motion more precisely. A longer orbital baseline will help determine the shape and period of its orbit. Infrared spectroscopy may provide clues about its atmosphere and internal heat. Every new measurement can change the picture. Perhaps the planet is more massive than expected. Perhaps its orbit is tilted in a way that explains the disk structure. Perhaps another, even smaller world is waiting in the remaining data. That last possibility is not science fiction. Planetary systems often contain more members than the first observations reveal. Detection depends on distance from the star, orbital orientation, brightness, and the sensitivity of the instrument. What looks like a complete system may simply be a system whose faintest layers remain hidden. Beta Pictoris teaches us to be cautious about that boundary. The map was never empty. It was incomplete. There is a poetic lesson here, but also a practical one. In astronomy, discovery is not always a dramatic new point appearing in a fresh image. It can be a pattern that has been waiting inside an old image, invisible until technology and imagination meet. A young star, a dusty disk, and a planet concealed for 11 years may sound like a small story compared with the scale of the universe. Yet inside that story is the entire process of science, observation, uncertainty, reanalysis, skepticism, and confirmation. Beta Pictoris is still changing. Its planets continue to orbit. Its comets continue to evaporate. Its debris continues to collide and disperse. Light from that system crosses interstellar space for 63 years before reaching our telescopes, carrying a record of a planetary system in the act of becoming. And now, within that record, we can finally see one more world. The next time a telescope points toward Beta Pictoris, astronomers will not see the same system they saw before. They will see a star with a wider family, a disk with a deeper story, and a reminder that the cosmos often hides its most interesting truths in the faintest signals. The universe is not silent. It is simply subtle. And sometimes, the world we are searching for has been there all along.